One interesting application of conductors in electric fields is their ability to shield what's inside of the conductor from external electric fields. Let's take a look at that a little more closely. If we have a region of space that's filled with a uniform electric field, and we take a conductive object and put it into that electric field, let's take a look and see what happens. The electric field will cause the electrons to move to one side of the conductor, leaving some positives behind on the other side. So the field lines terminate on negative charges and originate on positive charges, something like this. And our electric field will take this kind of a shape. Now think about what happens inside that conductor. There's an electron inside that conductor that's free to move, but it's happy sitting where it is. We take that conductive object and put it into some external electric field. That electron feels a force, and it wants to move because of that electric field. It wants to move opposite the direction of the electric field. So it does. Then the next electron says, I feel this external electric field. I want to move in that direction also. But there's already an electron over there repelling me. Well, the external field is bigger. It wins. I'm going to move over there also. Then the third electron says, there's this external field causing me to go in this direction, but there are two electrons over there pushing back on me. Well, the external field is bigger. I move over there. And this keeps happening until the force from the external field causing the electron to go in one direction is equal to the field caused by the electrons that have already moved, pushing it back in the other direction. And those two fields cancel out, and then the electron doesn't move. No more electrons move after that. That means that inside of this conductor, once we wait a little bit and allow the electrons to come to equilibrium, inside of this conductor, the electric field has to be zero. We know it's zero because it's in electrostatic equilibrium. The charges are not moving anymore. We can have electric fields inside of conductors, but it would cause the charges to move because that's the definition of a conductor. The charges inside the material of the conductor are free to move. If that conductor has an electric field inside of it, the charges will move, like the wires in our house that carry currents. There's an electric field in there. The charges move. That's the current that makes our electronics work. So when we take this conductive sphere and set it into the external electric field, for a short period of time, there is an electric field inside of that conductive sphere as the charges are moving and separating. Then eventually they stop moving and we're in electrostatic equilibrium. And that's when we know the electric field in the conductor is zero, because if it wasn't, charges would still be moving. And this is true even if our conductor isn't a solid conductor. It's true even if it's just a conductive shell with a hole or a cavity in the middle. So this part right here is conductor. And this is our hole or our cavity. And we take this shell and we put it into an external electric field. And we get something like this. The electric field lines terminate on the negative charges that move to the left side of our shell. They originate on the positive charges that are left behind on the right side of our shell. And in between, we have an electric field that's equal to 0. Not only is it equal to 0 inside of the solid conductive material that makes up the shell, it's also 0 inside of the cavity, inside of the hole in our conductor. Why is that? Because the electric field that's there from the external field that was present before we put our shell in that location exactly cancels out the internal field that's created by those charges that have moved. The negatives that have moved to one side and the positives that have moved to the other create their own electric field, and that cancels out the external field. If it didn't cancel out the external field, more charges would move. There'd be forces on those charges and they would keep moving. When do they stop moving? When the two fields exactly cancel out and the electric field inside the conductor, including the cavity, is 0. Let's take a look at this demonstration involving an electroscope. An electroscope is a combination of metallic pieces, conductive pieces. There's a top part right here, and that's connected to a lower portion. And there's a pivot point, and there's a needle that can pivot. There's our pivot point, and the needle can rotate. And all of those are electrically connected together. That's all conductive. The needle, the lower part, the upper part, those are all electrically connected together. Those are all conductive materials, and they are isolated from everything else. If I hold a charged object above my electroscope, let's make it positive. In this case, I have a rod that's positively charged. It attracts electrons to it. So what am I going to get? I'm going to get electrons up here on the top surface. That's going to leave positive charges behind in the lower portion of the electroscope, on the needle, on the arm. Well, positive charges repel each other. So that needle is going to rotate, because the positives that are left behind in the lower part of the electroscope repel each other, and that causes the needle to rotate. This is called an electroscope. It's used to indicate the presence of an electric field. Watch what happens when we bring this negatively charged PVC rod over it. Take it away, bring it back. Now, while the rod is over the electroscope, I'm going to ground the electroscope by touching it. And this time when I take the rod away and bring it back, the opposite movement is seen on the needle. Now I'll ground it again, and it's back to operating the way it did originally. As you saw in the video, when the charged rod was brought over the electroscope, the needle deflected, and when it was removed, it went back to normal, as I've shown here. But what happened when I touched the electroscope? When I touch the electroscope, I'm connecting it to ground. Ground is a reservoir of excess charge. So instead of the negatives coming from below and working their way up and leaving positives behind, like I've shown here, the negatives, the excess negatives, can come from ground. So the electroscope's lower portion can stay neutral, and excess electrons can fill the top plate. Then if I remove ground first, while that positive charge is over the electroscope, I've gained electrons. my electroscope now looks like this. The key is removing ground while the positive charge is still in place, attracting those electrons from ground. So I removed it and kept some of those electrons on the electroscope. Next, I'll remove the charged rod. What's going to happen to those electrons? In this case, the electroscope has excess charge. While the charged rod is over the electroscope, those excess electrons are being held to that top plate, and the lower portion is neutral. When we remove the charged rod, those electrons all repel each other. They spread out as far apart as they can over the electroscope. Some go down to the lower region. Like charges repel, and the electroscope rotates a little bit. When you put the charged rod back, those electrons are drawn up to the top plate, and the needle goes back to vertical. We just looked at a case where we took our conductive shell and put it into an external electric field and saw that it shielded the internal part of the shell from that external field. Now let's take a look at what happens if we do it the other way around. What happens if there's a charge inside of our conductive shell filling the space around it with an electric field? What does it look like outside of the conductive shell? Think about that for a second, and then come back and we'll talk about it. There's a positive charge at the center of that conductive shell, and it wants to fill the space around it with an electric field. What's it look like outside of the shell? I hope you've thought about it for a minute. Let's start with the conductive material itself. If there's an electric field present, the electrons inside of that conductive material are free to move. The electrons are going to move opposite the direction of the electric field because they're negatively charged. Positive charges move in the direction of the electric field. So the electrons are going to end up here on the innermost surface. When are the electrons going to stop moving to the innermost surface? When the electric field inside of that conductive material, inside of the shell, is 0. So when E is equal to 0, in that conductive material, then the electrons stop moving. Well, if electrons moved into the innermost surface, what does that leave on the outer surface? It leaves some positive charges behind. And what do positive charges do? They emit electric field lines. So if you're outside of this shell looking in, you don't even notice the shell there at all. You see the electric field from a point charge at the center of the shell. It's as if the shell is not there at all. But if you were inside the shell, inside that cavity, and the point charge was outside, you would not detect any electric field. You would be shielded from that electric field. So it's a one-way shielder. It shields electric fields from going in, but not from coming out. Now let's think about this for a second. Can you think of an example in your home where you have something like this? How about your microwave oven? When you look through the door of your microwave oven, you're looking through a metal mesh, and the microwave oven acts like a Faraday cage. This is called a Faraday cage, this shielding cage that prevents the electric field from going through. Acts like a Faraday cage. It shields the electric fields from getting out. How does it do that? It's connected to ground. So let's take a look at what happens if I have this conductor and I connect it to ground. Right now it's not connected to ground, and the electric field comes right through the conductive shell. Whatever electric field is being created on the inside by that point charge comes right through like the shell isn't even there. So what happens when I connect this shell to ground. The electrons come from ground now. They don't have to come from the outermost surface, leaving positive charges behind. Now they can come from infinity. They can come from this reservoir and enter and go to the innermost surface. So my conductive shell would look something like this. If you like to think of this the proper way and only the negative charges move, then when it's hooked up to ground, the negative charges could come from ground and go to the innermost surface and not affect the charges on the outermost surface of the shell. And so we get enough electrons to shield the electric field from within the conductive material, and because the conductor has an outer surface that doesn't have positive charges on it anymore, we get no electric field outside. So in this case, when that shell, when that Faraday cage is grounded, it can shield the electric field from coming out as well as going in. Sometimes it's easier to think about charges moving as both the positives and the negatives moving, even though we know that positives don't move. They're tied to the nucleus of the atom and only the electrons can move. But if we think of this as both the positive and negative charges moving, and we put a positive charge at the center, it's going to attract some negative charges to the innermost surface. The positives get repelled to the outermost surface. And as soon as we hook up ground, those positives can move even farther away from each other because they are repelling each other. They want to get as far away from each other as possible. They can go infinitely far apart by leaving the shell and going to ground. And so that's what they do. And you end up with a diagram that looks like this. The next question is, how much charge do we end up with on the inner surface of that shell? Let's think about that for a second. We know that charges keep moving into that innermost surface until the electric field in our conductor, in the conductive material, is zero. That means that we could draw a Gaussian surface here. I could draw a Gaussian surface inside of my shell, like this. And I can say the integral around that closed spherical imaginary Gaussian surface that I'm placing inside of the conductive material of the shell of E dot dA has to equal the charge inside the shell over our constant epsilon naught. And we know that E is 0. That means that our charge inside of the shell has to be 0. Otherwise, this doesn't work. I know I have plus Q at the center. So that means that on the innermost surface, I must have minus Q. Otherwise, they don't add to 0. Those are the only two places I can have charge in this scenario. The charge on the innermost surface of a shell, of a conductive shell, is always equal in magnitude and opposite in sign to the net charge inside the cavity. Let's see if you've got it. Let's look at this example. We've got our conductive shell. It has a net charge of plus 2 coulombs. So on our shell, plus 2. Inside of the cavity, at the center of the cavity, there's a negative 3 coulomb charge. And we want to know what is the charge on the inner and outer surface. Q inner and Q outer. What are those charges? If there was no charge in the center, if we got rid of that point charge in the center, all we had was a conductor with some excess charge, plus 2 coulombs of excess charge on it, what would happen? That excess charge wants to get as far away from the other charge as it can. It's all the same sign. It repels itself. So it all ends up on the outermost surface. If there's no charge inside the cavity, Q inner is 0, and Q outer is just plus 2 coulombs. But when we put the charge inside the cavity, it attracts some charge to the innermost surface. And we saw earlier that it always attracts an equal amount of charge, but opposite sign. So on the innermost surface, we're going to get positive charges. How many? 3 coulombs to cancel out this negative 3 coulombs. So Q inner is going to be plus 3 coulombs because Q inner has to cancel out everything inside the cavity, so we get E equals 0 inside our conductive shell, because we know that if this conductor is in electrostatic equilibrium, the electric field in the conductive material has to be 0. If plus 3 coulombs are on the inner surface, and this shell has a net charge of plus 2, what has to be on the outer surface? Q inner, the charge on the innermost surface, plus Q outer, the charge on the outermost surface, because charge always ends up on the surfaces of the conductors. We're not going to have excess charge in the middle somewhere. It's either going to be on the inner surface or the outer surface. We add up all that excess charge, and we're told it has to be the net charge on our conductive shell. This is plus 3. And so Q outer is minus 1 coulomb.